I want to make stuff make sense.
Earnshaw.
Oh, it's hot. The base level of
You end up why not? What's your other for? Oh, 3190.
I also have a problem if it's easy.
He likes it.
there's a lot of stuff.
I can tell you that. I've never done it either. This seems more fun. Maybe I'm wrong. I think all 5 might be a lot better. Yeah. It sucks we have to do so many. I wish we could start electives a lot earlier. 3190. Is it who's teaching this? Still Phillips. Yeah, he wrote the textbook stuff. It's a little. You'll like it. It's okay. No. Well, I took it last fall and all the exams were online. It's easy. The only hard part was no looping. Because you had to derive the. Yeah, that one's the only part you have to like really. I know. But besides that, I think whatever one we're doing next, SPM or whatever, that's going to be more tough. I looked at it too. You have to like derive the grade, which isn't that bad. Yeah. We'll see. I know. Well, they're all. It's funny because it's all like CS. It's the Stanford CS project, which is awesome.
Okay, let's get started. It's 3:40. I want to turn some time over right away here to Professor Tom Henderson to talk about the Deep Learning Certificate that the department is now offering.
Thanks very much. Yeah, hi, my name is Tom Henderson, and I'm just going to spend about 5 minutes talking about this. Let's see. So, last year the state decided that they wanted some deep tech programs, so they invested in some new certificate programs and other programs. Ours is a graduate certificate program, basically 15 hours, and you get a certificate that says deep learning, so you're certified in deep learning. The idea is that 9 of those would be things you'd normally take, and probably if you're interested in deep learning, you'd take them anyway. And then one of them is this, fourth one is this course, deep learning, and then there's a capstone course where we work with industry to do something of interest to people. So it's got multiple departments involved, so if you're in civil, mechanical, electrical, that's fine. CS is good too. We've got a number of associates in this thing. You can see some of them here. And so what happened is that we committed to provide working knowledge for students of what deep learning is. You'll learn a lot about that here. And to have, I call it an internship there, I should change it to capstone project, where we do a project here related to some industry interest. So what does working knowledge mean? Well, we busted up into what I'll call sort of the theory area in some sense, application areas, and then a deep learning course. So the idea is that you would take some from these, take this, and then there's a capstone course. So that's gets you your 15 hours. Why do this? Well, this is just Utah, the state. I went and looked for job openings in this area. There were about 1,000 related to this last year when we looked at this thing. So a lot of jobs in this area. You need to take one course at least from sort of these 3 CS areas. Although we allow, if there's something in civil or somewhere else that covers this material, we allow that as well. One at least from an applications area, and there are others than these. I just put some examples here. You have to take the deep learning course. Well, you're in that already. And then there's the capstone course. We offer it in the spring because you have to take this course before you take it. Okay. In fact, this certificate was approved to start this fall, but we had people take a capstone last spring. So the people who are getting this, there are 2 that'll get the award of the certificate already this semester. In fact, in the capstone course, we worked on some projects that the Department of Transportation in Utah was interested in, and we published 2 papers out of it. So you can also have some kind of academic side to this if you like. So almost done. NVIDIA, we have some partners on this. NVIDIA is one. Blency is one we work with a lot. We'd sure like to work with some other companies, a little closer to have them have projects, but Blency provided the projects this last time. And they're kind of a weird company that does a lot of sensor network stuff. If you drive your car into a parking lot, they can characterize your car by the signals emitted from the little radios inside your tires that tell the tire pressure. So they can identify your car with that kind of data. Kairos is another autonomous vehicle place. UDOT I mentioned, and some others. To give you an example, my student was working in this area, actually works for Blency, and they got a request from the state to find the barrels. So instead of Waldo, it's barrels. Like, where are our traffic barrels? They're lost out there in the state. They're never where the people say they put them. Well, you can buy dash cam images, because if you put a dash cam in your car, you may not know it, but that goes to the company that sold you the cam. They sell those images to departments of transportation. So you have a lot of images to train on. He trained on some images, spent 2 weeks, and within a couple of weeks, he had an app that tells Utah where every barrel is in the state. This is the kind of thing that the state's looking for, and so they're excited. Another area we're working on is autonomous vehicles, namely flying aircraft. So we're trying to coordinate all this, and there's a lot to plan on over the valley, putting roadways up there and having things go, so there's a lot of computation to do. Just another kind of example. We're talking to Goldman Sachs and other people, and we'd like to have all kinds of things. That's about it. You can apply. What I'll tell you is that if you have questions, really, you can send them to me because I'm heading this thing up, and I'm in CS. But moreover, there's, if you go to the CS webpage, they have, let's see if I can find this. There's a graduate link here, and if you go to graduate, they have certificate programs listed. And we're one of those. And in that, it tells you, there's not a lot to this other than the fact that there's a thing with some information about it, like what courses are possible to take, so on. And then there's a simple application form you fill out and just say, here's what I like to do for my courses to get my 15 hours. And that's about it. If you have questions, send them to me. I don't know if we want to take much class on questions, but if there's a quick question, maybe. Yeah.
If we took some of these classes as an undergraduate, if we took some of these classes as an undergraduate, is that okay for the certificate?
So long as you're matriculated in a graduate program. You have to, at this point, be matriculated. So you can actually be a BSMS, and that works.
Okay.
So long as it's, I think we normally put the 5,000 or 6,000 version. Yeah.
The capstone be combined with a graduate capstone project?
You mean in a department?
Well, yeah. Well, I guess what I'm saying is, like, if you're doing the project option for like your master's degree, right?
Oh.
Could you have it count for both?
That'd be up to you and your committee.
Okay, but that's
Just don't tell us about it.
Okay. Gotcha.
Well, you also work with a team on this, so I don't know, they'd have to say that they agreed to have a team do that.
Gotcha.
And that's me. Thanks very much.
Okay, so you're well on your way to getting a certificate in deep learning. See ya. That was that for me. All right. Welcome to class. Glad you're back. If you're interested in certificates, there you go. You're part of the way there. Yeah. I'm sure it's super valuable. All right, so we're going to get into our lecture day, but before we do that, just want to see if there's any questions about previous lectures. Raise your hand if you've looked at the homework. That should be everybody. You committed on day one to look at the homework. Okay. If you haven't looked yet, you're asking for trouble. You're going to get to the last week and you're going to be like, oh my gosh, it's too much homework. Don't let that happen. All right, we'll get started. So last time, okay, so today the topic is going to be on loss functions. Loss functions are a way of expressing our objective in terms of training our neural networks. But remember last time we talked about image classification, a lot of the challenges associated with that. We talked about machine learning and some of the basics in terms of how we would go about learning a model. We use k-nearest neighbors as a simple example of that. We got into linear classifiers. We talked a bit about how they're parameterized and then what the parameters mean in that linear classifier. So the rows of our weight matrix W, corresponding to a number of different things, decision boundaries in our high-dimensional space. Also, something like a prototypical example of the class itself as a data point in the set. We looked at those. We looked at not just the mechanics of it, so this algebraic point of view. And then we looked at we computed these scores with these linear functions, and we kind of just said, well, what we want them to be, we want the score, the output of this linear classifier to be highest for the correct class. So the question is, well, how do you get your linear classifier to do that? How do you choose the parameters, W, and then that offset B, to do that? Well, how's that done? Well, we're going to do this through through the framework generally of optimization, and so we need a way of specifying what our objective is, what we're trying to optimize, and this is the notion of a loss function. And loss, sometimes called like an error function, but it's really something that quantifies how, in general, how badly we're doing at the task. We want to reduce the badness, and we'll see that through some examples what we mean there. But then that's why the word loss is there. Where it's like, what are we losing in terms of how we're performing on this? Is another way to think about it. Okay, so that's where we're going to jump in today. So remember how we were doing this, like just a very simple example. 3 images from our data set, a cat, a car, a frog, and just some scores there, right? So this is the output from our linear classifier. At this point, we don't have our B, just our matrix W, and these are the scores. So if we were to put in this cat image, it's going to give us a 3.2 for cat, 5.1 for car, minus 1.7 for frog. Put in the car image, 1.3 for cat, 4.9 for car, 2.0 for frog, and we put the frog image in, 2.2 for cat, 2.5 for a car, and minus 3.1 for the frog. So, the question here is, are are these parameters right now good for classifying these images? No. If the objective is that we want the highest score to be assigned to the correct class, right? In the case of the cat image, the car has a higher score than the cat. In the case of the car image, it's actually correct. The car has the highest score. And in the case of the frog, it's the lowest of the three. It's minus 3.1. Notice that like whether the score is positive or negative really doesn't matter that much. What matters is, again, the order of these. Which of these scores is largest, and we want that to be for the correct class. So how do we kind of like encode this mathematically so that we can optimize our parameters to give us the kind of behavior that we want? And that's, again, the idea of a loss function. So we're going to look at these today. A typical way that this is set up, this is almost like everything we're going to do in this class will look like this. We're going to have, in the case of supervised learning, where we're trying to learn the labels for a data set. So the elements of the data set are the x's, the labels, the classes in this case are the y's. We have some sort of data set of capital M points, and our loss on that data set is just the loss, the average loss across the whole of the data set. So this is a loss for each individual data point. So again, the inputs here are our prediction. What does the model think is the correct class, and then here is the correct class. We make some sort of comparison here. That's what the loss function is doing. We sum that up over all of the data points. We divide by the number of data points, giving us the average loss over that data set. And that's, it's telling us, that's a number to tell us kind of how well we're doing at this task. Okay? All right. So, what are some examples of this? Well, here is an example. But just, you can look at this. Maybe it'll make sense to you right away, or maybe it won't. Just think about how you would want to do this. How would you express this objective of the correct score, or the highest score being assigned to the correct class? So one way of doing this is called a multi-class SVM loss, or oftentimes called a hinge loss. There's a reason for the hinge. We'll look at it in just a second. But the way that this loss is calculated is in this following way. So S's here will be for our scores, whatever our classifier is, whatever score it's assigning to the data point. And then the indices are going to indicate like in this case which data point, but in this case on the scores, it's going to be the score for the class, right? So we have this vector of scores that the classifier is giving us, and so these indices here on the scores will be indexing those classes. So we're going to run over all the classes J here, but this yi is one of the indices here, and it's for the correct, for the data point I, it's the correct class yi for that data point xi. Okay, and so what does this loss look like here? This SVM loss, this multi-class loss. Multi-class in the sense that this is more than just a binary classifier between two classes. This is 3 or 10 or 1,000 or 1,000,000 or whatever. You can formulate this. This is generic to all those cases. Well, remember what we want. We want it to be the case that if the score for the correct class is the highest, we want there to be no loss. Like we want to say like, hey, we're doing good on this example. And if it's not the case, if that's not the case, we want there to be some kind of loss accrued. And we basically want that loss to kind of scale with how badly we're doing, like how different the scores are, say, from like, the score for the correct class and the score for like some of the other classes that are maybe much higher. And this SVM loss is getting at that in a particular way. So it assigns a loss of 0 if the score for the correct class, remember this is an index for the correct class of the data point xi. If it's greater than j, the score for the class j, we're going to do this for each of the j's. Not this notation right here is a sum over all the j's not equal to the correct class. So we'll talk about that in a second. Don't get too hung up on it just yet. But we're going to make all these comparisons. So we're going to look at the score for the correct class. We're going to look at the score for some other class j. And we're going to assign 0 if the score is higher or greater than or equal to the score for the other class. But then we're gonna force something here for it to be a little bit bigger than that by some number. And here the number is fixed to 1. In general, you can make this any kind of positive number. And sometimes you might see this formulated with like an m here, because we often refer to this number right here as the margin. There's the margin in the sense of we want the score to be bigger than the score for an incorrect class by some margin, not just greater than or equal to, but greater than or equal to by some amount. And we call that the margin. So the margin's set to 1 here. In reality, you could set this to kind of anything, and then the scores would just like adjust themselves to the scale of the margin. Right? Like so the scale looks like the margin kind of provides units or something like that. But whatever, fix it to 1. So what we want is there will be no loss if the score of the correct class is greater than the score of an incorrect class, the class j, by at least 1. Okay? This is a formulation. We could have made this marginless. And we'll talk maybe a little bit in a second about why we want to have there be a margin. And if that's not the case, if this is not the case, then we're going to add something to the loss here. And it's going to be this, it's going to be what that difference is. So like, if this is not the case, then actually this score is less than the score of the incorrect class j plus 1. So this right here is a positive number, right? It's sj plus 1 minus something that's smaller than that. And so, anyways, that's going to be some positive contribution to the loss. And we're going to do this. We're going to go through each of the classes j, and we're going to do this comparison, and then we're going to sum all this up. So that will be the contribution to our average loss for the data point xi. And another way to formulate this, another way to write this like case statement here is with this max here. So the value we want to put here for that data point or for the class j is the max between 0 and this value. And you can see it's the same there, because if this is negative, then actually this is the case that this is greater than this, and so we want there to be a 0. And if it's positive, then we're in this case right here, in which case we want this part of it, and that'll be greater than 0 because it's positive, and so it'll be there. So anyways, these two things are equivalent. Okay, so like this is a loss function. This is an example of a loss function that expresses kind of again like how well we're doing at this task. If this is 0, if Li is 0, what is the case?
We're doing good.
We're doing good, but but in particular, what does it mean? How well are we doing?
There's a margin of 1 between all of the numbers, so the bold number is at least 1 greater than all the unbolded numbers
Yeah.
in that column.
Right, exactly. So if this ends up being 0, then the score of all the incorrect classes is less than or equal to the score of the correct class minus 1. Now, move that over in that case. Or said differently, the score of the correct class is greater than or equal to the score of any of the incorrect classes plus 1. So the score of the correct class is bigger than the scores of the incorrect classes by a margin, in this case 1. That's basically what you said. I just restated it 2 or 3 more times just to hear myself talk, I guess. But anyways, so there you go. So this kind of fits the notion of a loss. We want the loss to be 0. Oh yeah, and then if it's positive, that means that for at least one of the incorrect classes, the score does not satisfy this. So the score is within the margin of the score of the correct class. And that's bad. We don't want that to be the case, and so there's a bit of positive loss accrued there. And notice that if like this score for the incorrect class J is really large, then this contribution here is going to be really large, right? So like, this one is fixed. This is something, like call this fixed for a second, the score for the correct class. The score for the incorrect class, let's say it's like huge compared to this, to the score for the correct class. This is going to be a very, very large contribution. So it kind of, it scales, in this case, linearly with the difference between the score of the incorrect class and the score of the correct class.
So that one that we're adding, so you said that we could technically have any value there. So
any positive value.
Any positive value.
Yeah.
So I guess would it be fair to say that the larger that value is, that the more accurate we're expecting? Or
no, actually, that isn't what happens. You can basically, if this is like 100, you could divide everything here by 100, and you'd have your scores. You'd have the scores divided by 100. So like they're now rescaled to be 100th of what they used to be, and your margin's back to 1. So and that just is like it's like a change of units or something like that for the score, even though the score tends to be unitless. But
so does it not matter at all then what the value is?
In general, it doesn't matter what it is. I mean, it could matter if you make this really small within like the numerical tolerance of a machine or something like that, right? 10 to the minus 16 or something like that. But in general, like the practice is just set it to 1, and that just then determines kind of the scale at which the scores are going to be learned at. Yeah.
So if there are multiple incorrect classes that are within the margin of the correct class, do all of the
each one of those, each one of those. What did that just? Is that the?
Oh no.
Losing the bulb or something? Let's see how this goes. Light dimming, that seems bad. Blame this on Tom. I have no idea how I can do anything about that. This probably has nothing to do with it though, right? One thing I'm going to do is I'm just going to turn this power off and on, like the standard thing that we learned to do when we were kids. Yep. Feeling good about this. If it's too hot, it's too hot, and we're not, I don't know what we're going to do. Okay, eco mode. Eco mode probably means that it dims after a while. So I should probably just like maybe change the slides next time. All right. So so the question was about like if there's multiple incorrect classes within the margin, then yes, each one of those is going to make a contribution here, right? This is a sum over all the classes, all the incorrect classes. That's why we have this J not equal to the correct class. So each one of those will make a contribution here. Does that make sense? Yeah. So again, like this is not a bad loss function. Like for every incorrect class within the with the scores within the margin, we get a contribution to the loss, and it grows linearly with the the difference in those scores. And so like that basically means like the higher this loss is, the worse that choice of the weight parameters W is, the weight matrix W is, and gives us the notion of optimization that we're going towards. We want to make this loss smaller. We want to push it to 0. The larger it is, the worse it is, and a perfect solution is at 0. Good questions. All right. Any other questions? Light bulb working? This is sometimes called a hinge loss because of the way that this max function looks right here. So the wherever our Sj ends up being here, we add 1 to that, and for our Syi, if Syi is greater than that, then the loss for that particular class is, the contribution to the loss is 0. And as that score gets lower and lower, the contribution gets larger and larger in this linear fashion. And so that kind of looks like a Dora on a hinge or something. Creative, yes. Okay. So let's look at this for this particular example. Let's do the math here. So what loss do we get when we apply this SVM loss to these scores for the cat image? So we know the correct image, or the correct class is a cat. So we're going to do this. We're going to compute these things here, this sum here, but not for all the classes except the cat class. And you might be wondering why we exclude the cat class. There actually is explicitly we'll address that, but if you want to think about that now, great. But let's just do it. So let's just take. So we don't have an entry for the cat. Let's go to the car. The score for the incorrect class car is 5.1, and then the score for the correct class cat is 3.2. So we subtract 3.2 from 5.1 and we add 1. That's for the car class. And for the frog class, something similar. Again, we're going to subtract off the score for the correct class, and here's the score for the incorrect class, minus 1.7, and then add 1. So we do the math here. We see that this is 2.9. So we have max of 0 and 2.9. Do the math here. We see this is a max of 0 and minus 3.9. So we now apply the max operation. This is larger than 0, so we have a 2.9 here. 0 is larger than minus 3.9, so we have a 0 here. Add those two things together. The loss, the SVM loss for that cat image is 2.9 in this very simple example. Okay. Now there could have been a lot more classes, and we'd have a term for each one of those classes, but here we just have 3, because otherwise this would be far more boring than it is. But it makes sense? Okay. Yeah.
Do we need to try different numbers for the margin? Yes.
No, you don't need to try different numbers from the margin. Yeah. You could. So let me tell you why. If you did that now, that would change the loss, right? But in a learning scenario where you're learning the parameters to optimize this, the learning will basically take into account whatever the margin is. Like in essence, I've said this kind of different ways, different times, but in essence, it will take that into account and like scale the scores by that margin, and you'll get roughly the same solutions. Yeah. In this case, it would make in this static case, it would make a difference, but when we're learning, it will be taken into account via the learning algorithm.
So the margin doesn't reflect the accuracy that you're trying to learn towards, or?
Yeah, like in some sense it does, because like in this static case it does. It's like how much of a difference you want there to be. But in the scenario where you are optimizing the W, like all the parameters of your classifier, W and B, those will just adjust themselves. They'll arrange themselves in such a way that they're scaled by the margin. So it won't help you. So yes, in the static example right now, the larger you make this, like the more loss there's going to be. But in the learning example where you're iteratively, adjusting those parameters so that they do as well as they can on this, it won't matter. Cool. All right. Great. So before I even go to it, what's going to happen for the car image? What's the loss going to be?
0.
Why is it 0? I'm sure you're saying the right thing, but I can't hear it. Yeah.
We got it right.
Yeah, exactly. You got it right. The score for the car is at least 1 more than the scores for the cat and the frog. So like in this case, it got it right. So yeah, and we could do the math and show it, and there you go. Good. How about for the frog? Is there going to be 0 loss or positive loss? Right. Exactly, because it's actually the lowest score by a lot compared to like the margin, right? It's like 5 or more off. So we go through the math again. We can see, yeah, so it's actually more than that because of the margin now. Okay, so there you go. So a lot of loss here. So again, 0 loss here because I got it right. Some loss here because I got it wrong, but like not too badly. It's at least, like the cat was at least better. The score, the cat was higher than the score for the frog by at least 1. In this case, it's really bad, and notice that the contribution to that is much larger. Okay, so what do we do? So in this like massive data set of 3 data points, if we want to calculate the average loss, we would we take the individual loss for each one of the data points. We'd sum them up, we divide by the number of data points, and we get our average loss for the data set. And so now this is a single value, non-negative value, that tells us like something about how well we're doing on this task. So this is the idea of loss functions. Okay, what happens to the loss if the car scores changes a little bit? Let's just say like we had a little bit of jitter here, just kind of adjust these scores. Like this would be like a little bit of jitter in the W's, the parameters in W, and these scores just change by a little bit. How will the loss change?
Not at all.
Not at all. Is that what you said?
Yeah.
Yeah, you're exactly right. Because this score is way bigger than these scores. Like it's not just like at the margin, but it's like much bigger than margin. So a little bit of jitter won't change that. Those new jittered scores will still be, the car score will still be larger than the cat and frog score by the margin of 1, and there will be no change to the loss. That's actually an interesting property of this particular loss, that you can make changes to the parameters and see no change in the loss. That you can either think about it like there are arguments for why that might be good, there are arguments for why that might be bad. Like the insensitivity to the parameters when you're well beyond the margin. Anyways, good. Okay, what's the minimum possible loss? What's the maximum possible? So like, let's start with the minimum. What's the minimum possible loss? 0. Again, because each one of these contributions here is only ever non-negative. It's either 0 or positive. Good. So what about the maximum possible score? Yeah, it's unbounded above, right? Like we could imagine there being, W's such that this score is really low and this score is really high, and we can keep adjusting those W's so that we can keep stretching that out, like that difference between them. So yeah, really like, it can approach infinity, that loss. So it could be really, really bad. Good. Okay, this is an interesting question. So let's say we randomly initialize W, and it's small, meaning like all the entries in W are quite small, and therefore, because we have no offset, our constant B is 0, all of our scorers would be approximately 0 in that case, right? We're multiplying whatever X is by a bunch of small weights W, so the output of that product would be, approximately 0. So what is the loss in that case? Good, that's right. So in this case, these would be roughly the same, or they both be really small. So like the contribution here would be much smaller than the contribution of the margin, and so there would be a 1 for each of these. There would be a 1 in this sum. So each data point would give a loss of what? Approximately, in this case, what? Not 1, because there's 3 classes, and the sum is over 2 of the classes. So it would be 2. And then we're going to average that over, however many data points, 3 in this case. But they're all about 2, so you're going to get 2. So it's the number of incorrect classes because of the margin there. So good. And now finally to this question, we're excluding the class, the correct class when we do this sum here. But what if we were to add it in? What would happen?
Always be 1.
Yeah, always be 1, exactly. So we're always comparing to the score of the correct class. So if we didn't exclude this one, there would be a j that would be equal to yi. That yi would go here. These two things would cancel each other, and there would be a 1, right? So then there would always be a positive contribution in this case, right? So the loss per data point would be bounded below by 1. So it wouldn't. You can cope with that, like if you kind of know what you're dealing with. But it's sort of, you want the loss. It's nice and like parsimonious if like the loss is, its minimum is 0 and not like, 1 over the number of data points or something like that. So, anyways, it's that's why we exclude it. It's not contributing anything to our knowledge of like how well we're doing. So no need to track it. Good. Yeah. How about here? What if instead of summing all these contributions here, we actually took the mean over the number of incorrect classes? So in this case, we were to divide this by 2. How would that change things?
That's smaller than.
Say it again.
Just make it smaller.
It would just make it smaller. And would that matter or not?
Wouldn't it, it's the same argument for that adjusting the margin. It would just scale it up.
Yeah. So like it would basically divide everything by the number of incorrect classes. So yes, the absolute values themselves would be different, but like all of like the ranking would remain the same, right? That would be like an order preserving, kind of transformation of the losses, and we would still come to the same conclusions, right? Like we would still say that this set of parameters W is worse than this or better than this. And again, if the losses were the losses were all 0, meaning we had a W matrix where like we were doing this task perfectly according to this loss function, the dividing by 2 wouldn't matter. It would still be 0. So everything would basically stay the same, but it's like you're saying, it's just kind of like changing the units of everything, which doesn't really matter when making a decision about which W's are best. Good. What about this loss function? What if instead of just the max between 0 and this expression here, we squared that? So whatever was the max here, we then squared that value. How would that change things?
It would make the lossier ones have more weight, or would make the ones that are further away, the more affiliates, carry more weight?
Yeah, sort of. Squaring makes things smaller when it's less than 1, and then makes it larger when it's larger than 1, right? But so yeah, so for those things that were like really far, like were really bad, you'd see that they were like even further away. Would this matter in terms of the W that we choose via like this loss? Like, would this change the W matrices that for instance give us 0 loss?
Might kind of like allow for a whole bunch of images that are kind of mediocre and none that are very good.
And what do you mean by allow?
Well, it really might encourage, sorry, I don't know the terminology, but it might encourage models that can stay kind of close, but it's never accurate.
Because then we'd be making the loss smaller. Is that what you're? Yeah. In that case, like these losses are all small. We square them; they're even smaller, and then like somehow we prefer that.
Yeah. So I guess the easiest way to reduce the loss is to get rid of the really bad pieces while completely
Yeah. So it does have this interesting property where, like the contribution to the loss of the really good, like the cases that are accruing some loss but not very much, and the ones that are accruing a lot, changes, right? Like relative to each other, that does change. How about in terms of like the W's? So like, do we get a different set of W's that give us 0 loss?
The ideal W would still be the same.
Yeah, the sets of W's will still be the same. When we square zeros, we get zeros. When we square positive numbers, we get positive numbers. Squaring is actually an order preserving, operation again. So while this is true about the individual examples having different relative losses, compared to each other, so the incorrect classes within a particular image, overall, like for instance, we still get the same solutions to the loss equals 0 problem that we're like more or less trying to solve here. Good. Okay. Super easy to implement these things in NumPy and therefore PyTorch, JAX or whatever is your favorite. You might have already gotten to this. We want to all of our operations be as vectorized as possible, meaning that we get rid of loops. There's a lot of entries. There's matrices. There's lots of data points. We want to get rid of we want to get rid of as many loops as we possibly can when writing code, efficient code anyways, for computing anything here numerically, because those loops, we take a hit, especially in Python where you have, if you're not expressing types, for instance, and it has to, for every single one of those loops, look up the types of things. It's really, Python's notoriously slow for doing this kind of computation. And in general, vectorized expressions will be much more efficient than any kind of like looping operation because of all of those who went before us and programmed all that great Fortran code that all of our numerical computations still rely on under the hood, even under C. We usually work at Python as the API, and that has bindings to like C, and then C, the numerical libraries in that will most often have bindings to like Fortran, and that runs the fastest. And we want to take advantage of that code. It's been optimized and used, everywhere, forever. And so vectorizing our code makes sure that we take advantage of those kinds of optimized operations. And so here's an example of what we mean by that, where there's no loops in computing this. There's simply taking advantage of the fact that our NumPy, this right here is, import NumPy as NP. Our max is already vectorized, and this and NumPy already has ways of in a vectorized fashion indexing into our matrices of scores, W times this matrix of input, and And so we're just, at every level here, we're just taking advantage of the vectorization that already exists in libraries like NumPy, and to make sure that we don't add any additional loops in there. And your homework, again, spends a good amount of time getting you to think about this, writing loops code, removing some of the loops, and getting all the way to vectorized. And it can be kind of challenging at times to think about what these vectorized operations look like. In this case, it's fairly straightforward. You know, this vectorized operation looks a lot like the actual, you know, equation that we wrote down there, or the actual formula that we wrote down there. But other times it can be more complicated. Okay, so another important question: uniqueness of solutions. So in the loss function, we're trying to find a W that gives us zero loss. That's more or less like, that's the basic formulation of the optimization problem. We have a loss function that, when it's zero, that means that we've got the kind of solution we're looking for, and if it's non-zero, in this case it would be positive, there's something wrong, and we want to fix that, or we want to find a different W that will do better than that. So is W, so let's say we find one, and W is that one, it gives us zero loss. Is that going to be unique? Are there going to be multiple solutions? People are shaking their heads, no. Someone want to say something more about that? No? You're right, it's not unique. So if W is a solution, what's another solution related to W?
2 times W.
Yeah, anything times W, really. It's again this idea of like being able to factor out, like rescale everything. So yeah, 2 would do this, you know, n times W would do this. This is just kind of going through this example that we looked at before, where we had, you know, an example of zero loss. If everything were scaled by 2, we would still see that, you know, we were getting a zero contribution here because of this being essentially 2 times the previous solution. Okay, so is that a problem? Who's like taken an optimization class before? Really? No optimization class? Good. This will be your first optimization class. What's that?
It was on the convex.
Yes, right. Actually, that's good. I'm glad you said that. We like convex problems. Why?
Because they have, for any local minimum is a global minimum.
Yeah, exactly. Like, basically, if, you know, our minimum here is 0, and we found an example, if this were convex, we would know that that was like, that, you know, we were done. That was the unique solution. But we're gonna have a lot of solutions. In fact, when we start doing neural networks with, you know, tens or hundreds of millions of parameters or even more, we're going to be in this extremely high dimensional space, and the loss function itself will be extremely non-convex. Like, no one really quite knows. I mean, people have tried to apply kind of ideas from like statistical mechanics and these kinds of ideas from physics to sort of characterize these things. But the point is that we have an extremely non-convex loss surface, which poses a problem. It means that we've got lots and lots of solutions to our problem, or like lots of at least local minima that we're trying, that our optimization algorithms are trying to, you know, are trying to navigate to. We want to find the lowest one. That would be the best solution, but non-convexity provides a huge challenge. However, there are some ways at least to kind of start to combat this, and one of the ideas is through regularization, and we're going to get more into this in a bit in a different lecture. We're going to get into how we do regularization with neural networks, like what are some things that really work. But the idea of regularization is to, in addition to your loss, add to your loss another term that expresses some kind of preference for the weights themselves. Something about like some kind of prior expectation or belief about how the weights ought to be. And we literally like add that to our loss function. So we're no longer just optimizing just the pure loss, but we're optimizing that plus another term that expresses like how well our weights are meeting our sort of like prior beliefs on what the weights ought to be like. And again, we typically, these regularization terms are typically, like the loss, they're optimal at 0, and then anything greater than 0 is, we can do better than that. And so now we've adjusted our loss surface in some sense by adding this term to it. Perhaps it makes it a convex problem, not typically in neural networks, but it still can help us in choosing better weights. Now, what do better weights mean in like classification, for instance?
More general.
Yeah, more general, is that what you said? Yeah. So what does that mean? What does more general mean?
For example, if our model never seen the data, it can classify that data with our trained set that's already there.
Yeah. So maybe said a different way, we want our models to be general in the sense that we want their performance to generalize outside of the training set. So another way of saying this is we don't want to overfit our training data. This is one of the key themes in machine learning, right? Is that we have really powerful models that can learn to do a task really, really well, and that task is exemplified by our training data. Samples from what we hope is like the data, the data distribution that we care about. We have some labels for it, but we could overfit that in the sense that we could do really, really well on those examples, but do really, really poorly on everything else, or like, everything else sufficiently different. And this is actually like a really interesting and important theme, just generally in machine learning, especially in deep learning. And there's lots and lots of really interesting research in this area. But a typical way to combat this is through regularization. And the idea of regularization, this comes from the use of the word regular in math, which means to basically smooth out a function. So functions that are really, whose behavior kind of oscillates a bunch, or kind of, like changes a lot with small differences in the data, will typically, that's typically going to be worse than a function that is more smooth and therefore like interpolates between points more smoothly.
Yeah. So I guess with regularizing, you know what? Yeah, never mind.
Okay. If you think about it again, bring it up. So like, what do these regularization terms look like then? Oh, I didn't mention this. There's a parameter in there, lambda, and it's another one of these kind of scaling terms, right? It's a way of expressing a balance between the size of the loss and from the actual data loss and the size of the regularization. If we really want our parameters to be very regularized by whatever the formulation of R is, we'll get some examples in a second, then we want that lambda to be very high, because that means between the two of those, those two terms for the total loss, that one will be weighted higher, right? So you'll have to make the regularization term much lower before it's like balanced or on the same scale as the loss, and then vice versa. If we wanted the data loss to be the most important thing, then we'd make the lambda, that weight there, much smaller, and then the balance would be towards the data loss and so forth. And so you might say, oh well, lambda equals 1 it expresses the like an equal balance between them, and that's not necessarily the case. There's going to be a natural scale on which this average loss term is on, and a natural scale on which the regularization term is on. Think of it as this again as like some kind of abstract units, and if you want those to be balanced, you have to know what that is, what the expected losses and regularization values would be, and then you'd want your lambda to express like the appropriate ratios of those be balanced. Okay, so what do these things look like? So you've probably seen this a bunch if you've played around at all. in machine learning, there are often terms that look like this that we attach to our losses. So they take the names of like the spaces from which these metrics are derived from. L2 regularization is this sum of the squares of all of our parameters in the weight matrix. So each parameter in the weight matrix, however big it might be, remember we were looking at a weight matrix that was 10 by 3072, so there's 30,720 parameters in that case, in that matrix. So this is a sum over all of those. We'd square all those, we'd add them all together, and this would give us some, like, this would give us some number. And we would add that here with some weight, lambda, and then we would also be optimized. We'd want to choose W's where this was all smaller. So we'd want this term to be smaller. Same thing here, L1 regularization. This is similar, but instead of a squaring and adding everything together, we take the absolute values and add everything together. So each of these are giving us a positive contribution, unless what is the case? Unless the matrix W is which matrix? The zero matrix. That's the only case in which these regularization terms would be zero. So that's already kind of weird, right? Like if you add this on here, this term is pushing. If you take either one of these, and these are very common in practice. If you take either one of these and you put these on, add these to your loss, then you now have a term that's pushing your weights towards zero. Well, what's good about that? Like, do we really want a zero matrix? A zero weight matrix? No, that would be really bad in general. Like that would mean, like we would have chosen to have no response to the input in that case. We would just have our constant b. So that would be really bad. So why doesn't that happen? Well, that's true. The margin's over here, right? Is applying here. So there's no margin here. So like, if we didn't have this, we'd find that W equals 0 is the best thing. But we actually have this data loss term as well, and it's not likely that the best solution to the data loss is W equals 0. So they're kind of like contrary to each other, right? Like the individual way you would optimize either one is different from like what the combination of the two might be. And it's really, remember, it's the combination depending again on the weight parameter lambda, one of the hyperparameters here, that would determine kind of how much we'd want it to see our weights go to 0, or how much we'd want to see our weights give us 0 loss. And then another common a regularization term would be a combination of the L1 and L2 terms, again with some kind of weight parameter beta between them. Again, so you could kind of determine the balance between those two. So why are small? Oh, go ahead.
I was just going to ask, how does this help?
Yeah, how does this help? Why are small parameters good? So there's a slide next, so I'll get to that. There's like an illustration there. So we do use like L2 and L1 regularization are very, very common in training neural networks. But there are tons of other really cool regularization techniques that we will talk about. One is called dropout. Another is called batch normalization. There's like many of these others. There's very cool things like cut out, cut mix, mix up. We'll talk about some of these things that are used to, again, make your model more general, like able to generalize, to have better performance on data it hasn't seen before. So how does this work? Why regularize? We already said express preferences for weights. We make the model simple in some case. That's so it generalizes to the test data. That's the thing we're going to illustrate next and answer your question. And then we sort of said it at the beginning. We may actually improve our ability to optimize by adding curvature to make this a more convex, non-convex problem. All right, so we're not quite there yet. Let me just go to it so that So we answer the question. I'll get to that in just a second. So you might have seen this before when doing like a simple, even if you haven't taken an optimization class, you might have seen this before when like learning to fit polynomials, like the coefficients of a polynomial. You're given some data, and you're saying, okay, well, what is the polynomial that like goes through? You know, it's of a certain degree, and it goes through all of the points. So all of the points are on this polynomial. So you want to pick the degree, like the smallest degree possible, because that would be the simplest model, but not too small, because otherwise you won't be able to fit all the points. And so a perfectly fit model would be like this polynomial f1. It goes through all the points, but there's maybe a problem here, right? And here's the problem. In doing so, a polynomial is such that to fit all those, you're going to have to do a lot of the function has to do a lot of big turnarounds and things like that. And that actually corresponds to larger coefficients of the polynomial. And the trouble is that these just might be samples from a noisy data distribution, right? And in reality, there's really more of a kind of a smoother, more simpler explanation for the data that we want to find. And if you've ever done least squares optimizations for your for your data, you might have already run up against this where you allow for there to be some kind of noise in the sampling of the data points, and you might say, okay, well in that case, F2 is actually a much better fit. And the thing is how do we know? Well, if this is a better fit, this F2, we would find we would take data in our test set, and there's probably going to be some points in between here. So interpolation, there are going to be some points outside of here, and we would expect that the test data to kind of lie along this simpler explanation of the data rather than this. And you can see how forcing us to fit exactly this means that as soon as we say extrapolate here, move outside of our data points, we will probably have a very poor estimate of the performance there. This is just a simple kind of heuristic to kind of give you an idea. This is much harder to think about in very high dimensional spaces, parameter spaces. This is a parameter space of 5, not tens of millions. But the same applies. And so the way then to get this behavior, this smoother behavior, is to force the parameters of the polynomial here, or of our linear classifier or our neural network, to be smaller. That'll get rid of all of that'll tend to get rid of the kind of rapid changes as we slightly move from one data point to a nearby one. And that's the simple idea of regularization. So that would kind of generate. I was trying to address the question that you had, Katie. So do you still have a follow-up question?
No, I didn't.
Yeah, is that good? Okay, cool. And I think you had a question next.
Yeah, I did. I kind of have two now, but so I guess with regards to this, would the perfect function then be one where it goes up and then lines up on that sort of average line? Would that be the ideal?
Well, it's kind of hard to say, right? Because in reality we don't know, but in general we sort of expect there to always you might have heard of Occam's razor, right? So Occam's razor is you take two equal, or if you take two explanations of a phenomenon that equally explain the phenomenon, basically predict the phenomenon, or whatever, you would prefer the one that has a much simpler explanation. And why do we believe that? I don't know. Occam said it. It's worked well for physics.
I guess there's no one answer.
But in general, we prefer these because in practice, in doing this actually tends to give us better generalization.
Right.
You can test this for yourself all the time.
Right.
And it's also an expectation that our data points are not perfectly sampled. There's always noise in the data that we're looking at. And we don't want to fit that noise. We want to fit the signal and not the noise. Well, how do you tell the difference? Well, that's the subject of dozens of or hundreds, or I don't know how many, like PhD dissertations, right? But we tend to do this, and it tends to work really, really well. There are times where it could work really poorly. Maybe extrapolation ought to be down here, and this thing does better. You'll only know by trying it out.
Right. Sorry, I have another one.
Yeah.
So my original one was, so I know we did the cross-validation with the A&M. I guess my question is, like, how does that tie into this, or does it not apply, or maybe does every kind of algorithm have its own?
It does apply. Like you would use cross-validation to pick the hyperparameter lambda in this case.
Okay.
That's a hyperparameter for this.
Right.
And so this is an opportunity to use cross-validation to choose that. Now,
parts of the process.
You could also think of like the full regularization term itself to be a hyperparameter, in which case, you might have, R1 plus R2 plus R3, they have all their own weights, and you could do cross-validation across, all sorts of like combinations of those weights, including some of those weights being 0 to get rid of that term. So like it all kind of fits in the same framework.
Right.
Whether you can feasibly do that or not for large combinations of hyperparameters is another question. This is, if you remember, like when we were talking about this the last time, there was a comment on the slide that said we don't often do a lot of cross-validation in deep learning, and that's because oftentimes the learning takes so long. You can't really do true cross-validation, but you often do a little bit of cross-validation. You learn things like these kinds of hyperparameters and very important hyperparameters like the batch size, which we haven't gotten to yet, but your like mini batch size, your learning rate, things like that. And we'll get there. Slowly motivated. Yes.
You said you want to make the parameters the smallest. So in that example, you were talking about like quartic to cubic, and you're trying to make it like linear, right? Sort of.
Yeah.
Is that what you're talking about there?
Yeah. So there's like in a polynomial, there's kind of like for a polynomial of order n, there's n plus 1 coefficients, and then really the order of the polynomial itself is like another hyperparameter in some sense that you could also try to tune. But the important thing is that these wiggles in an n order polynomial come from having large weights, like large in absolute value. Like the way that you end up fitting something like this is that those coefficients end up being quite large. If they're quite small, then you will tend to be dominated by the parameter that is largest amongst all of those, like the order of the polynomial amongst those. Okay. And you can make it that way, like you can make it linear by that term being larger than the higher order terms of the polynomial, and something like that kind of applies in. It's not exactly the same. It's not close to the same thing, but like the idea applies for like the linear classifiers and the neural networks that we're going to look at. Like the larger those parameters are within our weight matrices, like for every layer in our neural network, the more opportunity there will be in that linear classifier or in that linear layer to like have wild kinds of behavior. And the wild we mean here is like very large changes in the output given small changes in the input. I don't know if that even answered your question.
No, that helps.
Okay, cool. All right, so I skipped over these slides, and we're starting to run out a little bit of time. So just on this notion of expressing preferences. So if we have this very simple example where we have a data point, it's all ones, and then we have two weight matrices, or in this case just weight vectors. One it's a 1, 0, 0, 0, and then the other which is all 0.25, so quarters. If you look at this and do the math, the product of your weight matrix with your input is the same in each case. So like in this very simple example, it's giving you the same output. It's like they're equivalent. However, if we add to this, an L2 regularization that it's preferring one or the other set of weights, which of these would it prefer? essentially which of these gives a smaller, which W1 or W2 does it give a smaller regularization term? W2, right? W2 does. W1 will give you a 1, and then it'll add 0. It'll be 1 plus 0, 0, 0. So you get a 1. In this case, remember you're squaring these, and this is less than 1, so you're going to get a quarter of a quarter. So you have a 16th, and you're going to add up 4 16ths, so that gets you back to a quarter, right? So in one case, in one case this term would be 1, that's W1, in the other case this would be a quarter, which is W2. So this would prefer W2. So notice what that's doing in this case is that it's spreading out. You have smaller weights, and that's kind of spreading it out throughout like all of the weight matrix. And in general, like that's kind of what would happen. Interestingly, you get sort of opposite behavior for an L1 regularization, where you actually sort of sparsify the matrix. You tend to get a lot of zeros. That's because of the geometry of L1 space. I'm not addressing that here, not because I didn't have slides on it, or I didn't have any slides on it. I would be happy to talk about that more if you wanted to, but we're running out of time. And I just wanted to introduce this idea in the last 10 minutes we've got, or 8 minutes we've got. So that was one kind of loss function, the SVM loss, the multi-class SVM loss. There are other kinds of loss functions, and one that we're going to see all the time when it comes to classification is this idea of a softmax classifier, sometimes called a multinomial logistic regression. And the idea here is that we want to take these scores and we want to think of them as probabilities over our classes. So we got to turn these into probabilities somehow. So how do we do that? Well, if you've been around, numerical optimization for a while, you already know, but this is a pretty common trick. The idea is right here, is we're going to take each of our scores, we're going to exponentiate those scores so that these become non-negative, or they become positive. And then we're going to divide by the sum of those positive numbers, and now we're going to have a probability distribution over our classes. And the way it looks is like this. We take our scores, we exponentiate them. So believe me that that's the exponentiation. So e to the 3.2, e to the 5.1, e to the minus 1.7. Now we're going to sum all those up and then divide each of those numbers by that sum. So now everything's going to sum to 1. This has gone to 0 because we're only tracking a couple of decimal points. And so now what's good about this is that you can interpret these as like the probability or the likelihood that this image is like of this class, right? So we can think of this as like the likelihood that so there's a 13% chance that this is a cat image. Of course, this is a cat image, so like that's too low for that. We need to adjust this. There's an 87% chance that it's a car, and 0% chance that it's a frog. So the weights are not good for this particular example, as we already pointed out, but this is the idea. So with that being the case, what we want to do is we want to take these probabilities, and we want a loss that's going to force us to increase this probability of the correct class, right? And oh yeah, by the way, these scores in this case, in a softmax classification case, you'll see the term logits referred to all the time. It's these scores in this example, and so I'm just pointing that out here. So what do we do here? Well, the common way to do this with probabilities is to turn this into a loss by applying the negative log to our probability. So we apply the log, and if you think about log so these are all probabilities, so they're going to be between 0 and 1. So if you think about what log looks like between 0 and 1, right? At 0, it's at minus infinity, and then it increases to 0 at 1, right? So that's almost right, except that it's negative. So we want to turn this around. So we multiply by -1. That's the negative term right here. so that instead of these all being negative terms, they're all positive terms. So now, if this is close to 0, this is going to be a huge number, and if this is close to 1, the probability is close to 1, this is going to be a very small number, approaching 0. So this has that kind of same kind of characteristic for the loss, where we want to see that for the correct class, we want to see that the probability of that is as close to 1 as possible. So 0 loss would express that the probability was 1 for the correct class, and because of the normalization, that would mean that it's 0 for all the other classes. And then if it was very large, then we would know we'd have a very small probability associated with that, and we would want that. We'd want to reduce that loss. This is a very, very, very common optimization methodology known as maximum likelihood estimation. This is the likelihood for the correct class, and we want to maximize that likelihood. So this is an estimate of the likelihood for this correct class, and we want to maximize that. And you know, this has theoretical grounding in like information theory, and so this is a very, very natural and appropriate way to express the loss here. So this is an MLE problem, a maximum likelihood estimation. And in general, if you can set up your optimization problem so that they are a maximum likelihood estimation problem, then you're much more likely to succeed in optimizing that than, say, other heuristics you might use, like this interesting hinge loss that we just looked at. In general, like, how do we think about doing this? We could. This is grounded again, like I said, in information theory, and this comes out of what we sometimes call cross entropy. Whether you might have seen this, you might have not. I'm not going to spend much time on it, especially because of the time. But the idea of cross entropy is that you're comparing two distributions together, and the cross entropy is smallest when the two distributions are the same, and that entropy is large and getting larger as these distributions are different from each other. And so, what distribution do we want to compare ourselves to? Well, the deterministic one, where all the probability is assigned to the correct class and no probability is assigned to the incorrect classes. And we can do that comparison. I'm just going to skip through this because it's not super important. Sorry. You can look at that in the slides yourself and have all kinds of fun hanging out with Shannon and friends. But the idea here is that when we do this cross entropy between these two distributions, we end up with exactly this term, which is again the maximum likelihood estimation. So we often refer to this loss as a cross entropy loss, and that's the reason why. But it's maybe perhaps easier to think about where this actually comes from when we think about it as a maximum likelihood estimation. This formulation of cross entropy becomes really nice when we start to mix labels, and we might have like multiple classes in there, and we might express like the ratio of like how much of the image the class takes up or whatever. But in general, this is a cross entropy. So great. So this cross entropy. Give me just one more minute. I apologize. What's the minimum of this loss right here?
0.
It's again 0. What's the maximum? You can go to infinity, right? As this becomes closer and closer to 0, this will be minus infinity times minus will be infinity. So again, you can go all the way to infinity. And then at initialization, where again like all the s's are small or they're all equal to each other, what's the loss? I just showed it to you. So in that case, the probability for every class would be the same. This would be like a uniform distribution. There would be if a number of classes is C, then the probability for any one class would be 1 over that. That's our uniform distribution. So we would have the negative of the log of 1 over C. That's just the log of C. And so, like, if we had 10 classes, you'd have that be approximately the natural base 2.3. Okay, so taking the examples that we've had already here in the class, we would, if we calculate the loss, via hinge loss or via cross entropy loss, we're going to get different numbers, but they have the same kind of meaning, which is 0 is like what we want to see, and anything greater than that is is an expression of we can do better. Like the scale that these are on is different. This is on like an information theoretic scale, so like this is on like a, you can think of this as being expressed in kind of in bits, which again makes it really nice for thinking about how the problem ought to be optimized. This is in terms of the scores and like the margin units, but so it's not as easy to interpret. And final question. In this case, we already answered this. So like, if we just talk about so think about the car example. This is like the car example. If in the case of the softmax loss, if we jitter again the weights, and that changes the score slightly, what happens to the softmax loss? It's going to change. It's going to change. So this is different from the hinge loss, where like if the hinge loss is like in this, like not in this case, this is right on the margin, so like you would see some changes, but in these other cases where it's really quite different, then it's not sensitive to that. But this one is always sensitive to changes, which actually gives it a kind of advantage when what you're trying to do in learning is to use that signal, like to use small changes as a way of saying which direction should we change the weights to make the weight matrix better. So this actually has like slightly better properties in that sense. Okay, that's it. We're done. Thanks for sticking around for a couple of minutes. Happy to answer questions.